Hi all. So today in chapter 8a, we are going to discuss about one-way analysis of variance, or to be specific, ANOVA. Right, first of all, we are going to understand what is experimental design. So experimental design is determines the way that a sample is selected. In a design experiment, the experimenter imposes one or more experimental conditions on the experimental units and records the response. An experiment is designed that will test the hypothesis. So this experiment will allow you to change some conditions or variable to test your hypothesis. So what is experimental design? So experimental design is, in a simple way, is approach, is experiment approach on how we are going to test our hypothesis. So by using this experimental design, we can make sure that our test or our hypothesis test is going to be accepted or fail to be rejected. And in experimental design also, it is can be referred to the approach that will allow us to change uh, what is the results or the conditions or the variable that need to be changed in based on your result of hypothesis. So that is experimental design. That is the way on how we are going to uh, conduct uh, our analysis and how we are going to interpret our analysis. So that is experimental design. Right, in experimental design, there are a few uh, there are a few terms that we need to understand before we proceed to our analysis. So the first one is the experimental unit. So what is experimental unit? So experimental unit is the object on which a measurement or measurement is taken. So it refers to the object or the things or the subject that you want to measure. So anything that you want to measure is referred to experimental unit. And the second is a factor. So a factor is an independent variable whose values are controlled and varied by the experimenter. Okay, so a factor is referred to the independent variable. And then a level. So a level is the intensity setting of a factor. So it depends on the level or the intensity based on the independent variable. And then a treatment. So what is a treatment? So a treatment is a specific combination of a factor's level. And then the response. Response is the variable that being measured by the experimenter. And the last one is the degree of freedom. So in statistics, the DF or the degree of freedom is the number of value in the final calculation of a statistic that are free to vary. So never mind, we are going to see the examples on how to detect what is the experimental unit, what is the factor, the level, the treatment, and the response. All right, let's see this first example. A group of people is randomly divided into an experimental and a control group. The control group is given an aptitude test after having eaten a full breakfast. The experimental group is given the same test without having eaten any breakfast. So in this question, it said that a group of people is randomly divided into an experimental and a control group. So that means a group of people, okay, was divided into experimental group and the other one is control group. Okay, the control group is given an aptitude test. So this control group is given a test, right? We given a test after having eaten a full breakfast. So this one having breakfast. Having breakfast. And then the experimental group, this one, the experimental group is given the same test. Also has been given the same test, but without having any breakfast. Okay, so that means both group has been given a test, but the difference is just for the control group, the test is conducted after the group is after the group is having their breakfast. But for experimental group, the test will be conducted, but without the group having breakfast. Okay. Now, what is the experimental unit in this question? So, if you refer to the previous slide, as I mentioned that the experimental unit is refer to the object or the subject that we want to measure. So, in this group, what is the subject or the object that we want to measure? So if you refer in the first sentences, it states that a group of people is randomly divided into experimental and a control group. So the experimental unit must refer to a group of people. So the subject or the object that we want to measure is people. So the experimental unit is a person. And now what is the factor? So factor is referred to the independent variable. So what is the independent variable in these questions? So in this question, it states that the both groups is the both group is tested when they have breakfast and without breakfast. So the independent variable here is breakfast. So if refer to breakfast, it must refer to the, breakfast is full breakfast, this one full breakfast, and the other group is without breakfast. So when we talk about breakfast, it must refer to the meal or the food. Okay, so the factor here is meal. And what is the response? So the response is the variable that being measured by the experiment. So we want to score we want to measure the test. So the response is score on the test. What is the level? So the level is related to the factor, isn't it? Because the level is referred to the intensity of the factor. So the factor is the meal. So what is the intensity of the meal in this question? It is breakfast and no breakfast. So the level is breakfast or no breakfast. And the last one is treatment. So what is treatment? If you refer to the terms, the treatment is referred to the specific combination of the factor levels. So it is either breakfast and no breakfast. Okay. All right. What if the same questions, but now the experimental in the previous example also record the person gender. In the previous example, all right, it records the uh, test for the group of people that having breakfast and without having breakfast. So that is referred to the meal. But now, in the same situation, in the same experiment, but they also record the person gender. So what is the factors, the levels, and the treatment? So the experimental unit is still the same, that is person. Okay. And the response is also same, that is score. Now, the difference is the factor. The previous experiment, there is only one factor, isn't it? That is meal. That is meal. Meal. But now, in the same experiment, it also record the person gender. So it refers to the gender. So the second factor is gender. So if the male, the level for the factor 1 is breakfast or no breakfast, okay, but what is the level for factor 2, that is gender? Because gender, we only have two groups, isn't it? That is man and woman, or male and female. So the level for factor 2, that is gender, is male or female. Okay, so the level is the intensity based on the factor or based on the independent variable. So now in this experiment, the independent variable is male as the previous slide. And now in the same experiment, right, they record the person gender. So gender will be the second independent variable or the second factor. Okay, because gender only have two groups, so the level to measure the factors is only male and female. So what is the treatments? The previous treatment is breakfast and no breakfast. But now we have another factors, that is gender. So we must add also the treatment for the second independent variable, that is male and female. So the treatment now will be male and breakfast, female and breakfast, male and no breakfast, and female with no breakfast. Okay. Alright, that is experimental design, the basic what we can understand about what is experiment. Okay, what is experiment? So that is the experiment when we want to measure the subject or the object that we want to measure based on the specific or systematic analysis. That we must recognize what is the treatment, what is the factors, what is the levels, and what is the response. Okay, now we are going to discuss about one of the experimental design, that is the analysis of variance, or known as ANOVA. So what is the analysis of variance, or ANOVA? All right, first of all, what is variance? What is variance? Okay, so variance is variance in statistics is a measurement of the spread between numbers in a data set. Okay, so variance is a measurement of the spread between numbers in a data set. So that means it measures how far each number in the set is from the mean, and from every other number in the set. So that is variance. So variance is when we want to measure the spread between the numbers in our data set. So now, what is the analysis of variance or ANOVA? So analysis of variance, ANOVA, is referred to analysis tool that is used in statistics that will split the observations on the variability inside the data set. Okay, so usually the analyst, okay, or the researcher will use the ANOVA test in order to determine the influence that independent variables have on the dependent variable. So usually why we conduct the analysis of variance or ANOVA is because we want to test the influence of the independent variables towards dependent variables. Okay, basically actually this ANOVA is extended from the T test or the Z test that we have discussed in our previous lesson. Okay, actually the T test or the Z test method is proposed in early 1918, right, by the founder for the T test or the Z test method is Ronald Fisher, right, in early 1918. So he created the analysis of the variance method. But through the times, right, in early 1925, this Ronald Fisher, Ronald Fisher, he found that the analysis test is not only can be used by using the T test or Z test, and he believed that it must be beyond that. So he introduced the analysis of variance or ANOVA, all right, in early 1925, and it was being well known and being well used until nowadays. Okay, so that is the basic understanding on what we can see in the analysis of variance or ANOVA. Okay, so the analysis of variance is an experiment that has been properly designed, as we discussed, and we are going to use the analysis of variance when we want to know the we want to test the variation in the groups. Okay, so it can be it can have factor 1, as we see in our previous examples. It can be 1 factor, 2 factor, or maybe more factor. Okay, so in the analysis of variance, if you see here, okay, the variation is stated that the variation between the sample mean is larger than the typical variation within the mean. So this is the conditions, the example of the conditions, if the variation between the sample means is larger than the typical variation within the samples. Okay, but now this is the example to show that when the variation between the sample mean is about the same as the typical variation within the samples. So it's going to be like this. Okay, it's going to be like this if the sample mean is almost the same as the typical variation within the samples. But if the variation in between the sample mean is larger than the typical variation, then the condition is going to be like this. Okay. So what we can conclude about the analysis of variance or ANOVA. So the assumption that we can make for ANOVA is the observation within each population are normally distributed with a common variance, and the assumption regarding the sampling procedure are specific for each design. So analysis of variance procedure are fairly robust when sample size are equal and when the data are fairly long. So we can conduct this ANOVA test when we have the same sample size for both or for every group or each of the group. All right, so the sample size must be equal, and when the data is mount shape, that is in the normal distribution shape. So when our data is in normal distribution and we have the same sample size for each of the group that we want to test, so we can conduct the ANOVA. So what is ANOVA actually? So ANOVA is the test to find out if the survey or the experiment results are significant. Or in other words, they will help us to figure it out if you need to reject the null hypothesis or accept the alternative hypothesis. Okay, so basically what is the difference between the ANOVA and our previous discussion regarding the t-test or the z-test? Okay, usually in t-test, we are going to conduct the t-test or z-test when when we want to compare the two treatment means. That means it has the one sample mean or the two sample mean. But what if we have more than two treatments or more than two groups? So if we want to make a comparison that when we have more than two groups or two treatments, so we must use ANOVA, because the t-test or z-test only limited into one or two sample. So if we want to measure more than two treatment means or more than two groups, that is maybe 3 and more, so we must use ANOVA. Okay, so that is the difference between the t-test and z-test and ANOVA. So that is why we are going to use ANOVA. Okay, and again, I want to remember, if we have the sample size that is less than 30, so we can use the t-test or t-distributions. But if we have the larger sample size or more than 30, so we are going to use the z-test or z-distribution formula or z-distribution calculation to get the analysis. And if we have more than two treatment means or more than two groups, then we must use ANOVA. Okay, because the z-test and t-test only the comparison between two groups or two treatment means. Okay, so in the analysis of variance, or known as ANOVA, they are also divided into two types. That is one-way ANOVA, and the other one is the two-way ANOVA. Okay, basically in one-way ANOVA, the test will allow us to make comparison between the means of 3 or more groups of data. Okay, so the number of independent variable is usually only 1, but two-way ANOVA, the independent variable is 2. Okay, And in one-way ANOVA, the means of 3 or more groups of independent variable on a dependent variable. But in two-way ANOVA, the effect of multiple groups of 2 independent variables on a dependent variable and also on each other. So the number of group of sample for one-way ANOVA, that is usually 3 or more. And for two-way ANOVA, each variable should have multiple sample. Okay, but now in this chapter, we are going to focus on one-way ANOVA. So for two-way ANOVA, we are going to discuss in our next lecture. Okay, so that is one-way ANOVA and two-way ANOVA. Okay, for one-way ANOVA and two-way ANOVA, we are going to use these two designs in order to conduct our one-way ANOVA analysis and two-way ANOVA analysis. So the first one is the completely randomized design, or CRD. Okay, so CRD is actually also known as one-way ANOVA, and the completely randomized block design, or CRBD, is also referred to the two-way ANOVA. So CRD is one-way ANOVA. Okay, one-way ANOVA. But CRBD is the design that has been used to conduct the two-way ANOVA. Two-way ANOVA. Okay, so now in this chapter, we're going to focus on the CRD, or the one-way ANOVA. So what is the completely randomized design, or CRD? So CRD is a one-way classification in which one factor is set at a key different levels. For example, factor is male. Okay, factor is male. And K are K1. K may be referred to K1 as no breakfast, and K2 as light breakfast, and K3 as full breakfast. So K is the population mean. So are the K population means the same, or at least one mean different from the others? So that is the assumptions, or the situation why we want to why we need to conduct the CRD designed in one-way ANOVA analysis, because we want to measure either the mean in the population based on the three populations mean, that is no breakfast, light breakfast, and full breakfast. We want to know either at least one mean is different from the others, or otherwise. Okay, so this is only the picture that they have illustrated that to show you that how if at least one, this is at least one mean is different from the other means. Okay, it can be maybe this K1 maybe different from this 2, or maybe this one, the K2 is different from K1 and K3. Okay, so that is the situation when we measure the one-way analysis, one-way ANOVA, or one-way analysis ANOVA by using the design CRD. So what is the assumption that we can make? So randomness and independence of error is independent random samples are drawn for each conditions, and the normality we usually assume that it is normally distributed, and the homogeneity of the variance is where the populations have equal variances. Okay, that is just the assumptions about CRD design. Okay, So this is about CRD. Okay. So random samples of size N1, N2, and until Nk are drawn from K populations when means or mu1, mu2 until mu Kn with common variance. That adds IJV, the jth measurement, replication, and the ith sample. The total variation in the experiment is measured by the total sum of square. So, what is the CRD? Okay, so it is about the total sum of square. But never mind, we are going to see the examples so we can more understand about what is CRD design in one way, ANOVA analysis. Okay, so let's discuss and see about the first example. Okay, is the attention duration of children affected by whether or not they had a good breakfast? 12 children were randomly 12 children were randomly divided into 3 groups. 12 children randomly divided into 3 groups and assigned to a different meal plan. So they have the 3 groups with different meal plan. So this is the 3 group. The number of breakfast, the light breakfast, and the full breakfast. So the different 3 groups. And 12 children. So we have 4, 8, and 12. So 12 children were randomly divided into no breakfast, light breakfast, and full breakfast. That is the 3 group. And the response was attention duration in minutes during the morning reading time. So the question is here, is the attention duration of children affected by whether or not they had a good breakfast? Okay, so this is the questions. Okay, when we talk about ANOVA also actually, okay, it focuses on the measurement of the variance between the groups and variance within the groups. Okay, so the variance, when ANOVA is focused on the test of variance between the groups and variance within the groups. So what is the test that is variance between the groups? So variance between the groups mean between, for example, in this example, we can see the 3 groups here. 3 groups, no breakfast, light breakfast, and full breakfast, isn't it? So this is what we can refer, these 3 groups is what we can refer as the comparison or test of variance between groups. Okay, between groups. Okay, what is the conditions where we want to test the variance within the groups? So within the group is like in this example is like this. So this is the within the groups. That means for no breakfast, we have 8, 7, 9, and 13. So that is the comparison within groups. So this is comparison between within groups. Okay. So this one is comparison within groups. Okay. So remember also in ANOVA, okay, in ANOVA, we are going to test the measurement of or the variability between the groups, okay, between groups, and the other one is when we want to conduct the test, when we want to compare the variance within group. Okay, so ANOVA is focused on test for variance between the groups and test for variance within the groups. Okay, so the larger the ratio is F. Okay, that is F. If in a t-test or z-test, we refer to Z. The test statistic is Z. But in ANOVA, the test statistic is referred to F. Okay, so the F is the ratio of how to calculate the ratio of F statistic is when between group, okay, divide by within group. Between group divided by within group. Okay, now in ANOVA, when this is the ratio, okay, the value of F. Okay, so the larger the value of F or the ratio, okay, so the more likely it is that the groups have different means. That means the larger value of the F or the ratio of the F value, so that means the higher chances that we can reject the null hypothesis. So that means that is the difference. The higher value of the F statistic, the higher chances that the test have the different significant mean or different significant effects. So the higher chances also we can reject the null hypothesis. Okay, and if most of the variation is between groups, okay, if most of the variation is between group, then there is a probability or the probability of a significant effect. But if most of the variation is within group, okay, so there is the possibility that there is no significant effect. Okay, all right, let's now we focus back on this example. Okay, so this is the example of the questions for ANOVA. As we discussed, it has been divided into 3 groups. That is no breakfast, light breakfast, and full breakfast, with 12 children. With each group have 4. Okay, so the no breakfast, light breakfast, and full breakfast is the between groups, and this one is within groups. Okay, so what is the treatment here? So the treatment is referred to K. So there are going to have 3 treatments. Okay, 3 treatments. That is no breakfast, light breakfast, and full breakfast. So 3 treatments. So K equal to 3 treatments. So now the question is, are the average attention spans are different? So are the average attention span different or not? Okay, but first of all, I will have a strong recommendation to all of you to draw the table first, the ANOVA table of the CRD, because if you draw this table, it will help you to more understand, and it will provide you a clear explanation of clear conditions what is the value that you need to calculate and based on the this table. Okay, so first of all, please draw the table, the ANOVA table of CRD. Okay, and then this is the formula that we are going to use in one-way ANOVA or CRD design of analysis. Okay, the ANOVA table of CRD is referred to the source. The source we are going to divide into the treatment and the error. The treatment is the treatment and error. So the treatment is usually also referred to the between group. Between group, and error is within group. Error is also referred to within group. Okay. So the F degree of freedom. So degree of freedom for treatment or between group is referred to K minus 1. That is the treatment minus 1. And how to get the degree of freedom for error or within group is the value of sample minus K. Sample minus treatment. And the total is the sample minus 1. So SS is referred to sum of square. So to get sum of square for treatment, that is known as SST. And sum of square of error or within group is known as SSE. Okay, and means MS is referred to mean square. So how to get mean square? So the value of SST divided by K minus 1, and how to get the mean square for error or within group, that is SSE divided by N minus K. And the final important part is we want to get the test statistic of F. So how to get this test statistic of F is MSC divided by MSE. Okay, so it is to get the value of test statistic of F, that is MST divided by MSE. So first of all, we are going to get all these value. The value of degree of freedom, both treatment and error, the value of sum of square for both treatment and error, and also the value of mean square for both treatment and error. Okay, so that is why it is important to draw the table because we can see what are the value that we need to insert in this table to get the final value of F test statistic. Okay. So this is also the how we are going to compute the formula. So the total sum of square is when the sum of squares of all values minus CM. So what is CM? CM is common mean. Okay, we are going to see the examples what is referred to common mean. Okay, CM, common mean, is also referred to CF. So CF is known as correction factor. Okay, and then we are going to get the value of CM. So how to get CM or common mean? That is G square divided by N. Okay. G square is also known as grand total. So grand total of all N observations. Okay, divided by N. So the second is SST. So how we are going to get the SST? The value of the total of all observations. The value of all total of observations minus the value of Cn. Okay, minus the value of Cn. And then what is SSE and how to get it? So the total of sum of square minus sum of square treatment. Okay. So this is the explanation about the ANOVA table of CRD. So the total sum of square is divided into two parts as I mentioned. That is sum of square of treatment or SST and the sum of square of error SSE. Okay, so to get total sum of square SST plus SSE. So this sum of square is also behave like numerator of a sample variance. When divided by the appropriate degree of freedoms, each provide mean square and estimate of variation in experiment. So the total DF, how to get total DF? The total DF is where the treatment DF plus error DF. Okay, degree of freedom. All right, but I also want to remind you that in this ANOVA analysis, we are going to refer to F table. Okay, F table. I have upload the F table, and the other table is Taki table in the Putra Blast. So you can refer and upload the F table and Taki table in Putra Blast. And okay, if in test or Z test, we are going to refer to the we are going to refer to T table or Z table. Okay, but now in ANOVA, okay, in ANOVA, we are going to refer to F table and the other one is Taki table. So I want to remind you that in F table, they are going to give you the two conditions. Okay, at the above one is the degree of freedom of E numerator. E numerator. So the degree of freedom of E numerator is referred to the degree of freedom between groups. Okay, between groups. And this area, okay, this area will give you the degree of freedom of denominator. Denominator. So the degree of freedom of denominator is referred to the degree of freedom within group. Okay, within group. So E numerator here is referred to between group, degree of freedom between group, and degree of freedom denominator is referred to degree of freedom of within group. Okay. So based on the question, the examples that we have seen in slide 13 in our previous slide. Okay, so first of all, it is more easier for us to compute or to get the average of each group. Okay, so we can label it as maybe T1 mean, T2 mean, and T3 mean, sum of mean. So how to get 37? That is 8 plus 7 plus 9 plus 13 and divide by 4 because we have 4. So we get 37. And same here for light breakfast. How to get 59? 14 plus 16 plus 12 plus 17 and divide by 4 because we have 4 mean here. So we get 59. So what is the basic formula for mean, to get mean? The basic formula to get mean, if you refer to chapter 1, okay, an introduction to statistics, the basic formula to get mean is the sum divided by the count, isn't it? So the sum is, for example, no breakfast, the sum is 8, 7, 9, and 13, and divide by the count. The count we have 1, 2, 3, 4. Okay, so how to get the mean for all these three groups? We must add all the value of the number that have been given and divide by the number that will be count. Okay, so full breakfast, how to get the mean of 53? 10 plus 12 plus 16 plus 15 divided by 4, then we get 53. So now we can get the grand total. The grand total. So the grand total is 37 plus 59 plus 53. So the grand total is 149. So if you refer back to the in slides 15, all right, if you refer to the formula, so how to get the CM? So the CM is also known the grand total square divided by n. So how to get grand total square divided by n or CM? Okay, so CM, we must get the sum of all square of all the x value divide by n. So how to get CM? CM, if you refer to the formula, okay, it is grand total G square divided by n, isn't it? Okay, so the grand total we get now is 149. So 149 square divided by n is 12. We have 12 students, isn't it? 4, 8, and 4 plus 4 plus 4, so we get 12. So 149 square divided by 12, then we'll get 1850.0833. Okay, now that is the first step. We get the value of CM. Now, the second step, we are going to get the value of total sum of square. So how to get the total sum of square? So if you refer also to the formula in slide 15, to get the total sum of square is when we need to sum of squares of all x values and minus with CM. So now the total of value is 8 square, this one 8, okay, 8 square, okay, and then you 8 square, okay, and then you plus with 7 square, this one 7 square, and then you plus with 9 square, plus with 13 square, plus with 14 square until 15 square. Okay, until 15 square. And then minus with CM. What is CM? CM is 1850. So the total is the total of SS is 1973 minus CM is 1850.0833. Then you will get 122.9167. Okay. And now we are going to the third steps. That is the value of SST. So how to get SST? So how to get SST? If you refer also to the formula in slide 15, the formula to get SST is the total value of uh, the total value of all observation in the sample and divide by n minus cm. Okay, so the total value is the total value of the sample is 37 square divided by 4. Okay, this one we have 37 okay, square divided by 4, and then plus with 59 square divided by 4. This one, second group, 59 square divided by 4. We have 1, 2, 3, 4. So divide by 4. And then 53 square divided by 53 square divided by 4 is this one for the last group, that is 53 square divided by also 4 sample and minus with cm. So the total is 1914.75 minus cm. Then you will get the SST is 64.6667. Okay, now we are going to the next steps. Next steps, we must find the value of SSE. So how to get SSE? So if you refer to the formula in slide 15, SSE is the total SS minus SST. So the total SS is this one minus with SST, this one. So 122.9167 minus 64.6667, then you will get the SSE is 58.25. Okay, now you have get all the value, the CM, the total SS, the value of SST, the value of SSE, the value of G. Okay, so you can start to convert all this value in the ANOVA table. Okay, so you convert all the value in ANOVA table. Okay, in ANOVA table. Okay, how to get the value of degree of freedom for treatment, the F of treatment. So if you refer to the in previous slides, in the table, all right, in the general table, the simple formula to get degree of freedom for treatment is K minus 1. So now the value of treatment or K is equal to 3. So 3 minus 1, okay, this one you will get 2. This is K minus 1. So K treatment is equal to 3. So minus 1, so we'll get 2. So how to get the degree of freedom for error or within groups? So to get the degree of freedom for error or within group is n minus k. So now n, we have 12, isn't it? 12 students. So n 12 minus k. K is treatment 3. So 12 minus 3, then we will get 9. Okay, so the total value 9 plus 2 is 11. Okay, so the value of SST, okay, as we have calculated before, it is 64.6667 and 58. Also, we have calculated, so just insert in the table SST, SSE. To get the total, just plus the value SST and SSE. Okay, and then for mean square MS, MS is, if you refer also to the general table, And the simple calculation show when we want to get the MST, the value of SST divided by K minus 1. Okay, so this value is when you get from SST divided by K minus 1. Okay, so SST here 64.6667 divided by K treatment is 3 minus 1. So you will get 32.3333. Okay, so how to get MSE? This one. So to get MSE, if you refer to the general table in the previous slide, the simple formula to get MSE is SSE divided by N minus K. Okay, so when you calculate this, you insert the value in this formula, then you will get MSE is 6.4722. And now the last one, the test statistic of F. So this is the important part when we want to get the value of F, test statistic of F. So how to get F? If you also refer to the previous slide in the general table of ANOVA, the simple formula to get F is MST divided by MSE. Okay, so MST here divided by MSE. So you will get 5.00. Okay. So as it is same as in t-test and z-test in our previous lesson. When we want to present our analysis or our result, first of all we need to mention the null and the alternative hypothesis. So what is the null hypothesis? The null hypothesis is when we assume that all is same, no different. So now the null hypothesis is when mu1 is equal to mu2, mu3 until mu k. And for H1 or HA, alternative hypothesis, we will usually predict the situation where it is contra from the null hypothesis. So we will predict that at least one mean is different from the other. Okay, at least one mean is differ from the other mean. So that is the hypothesis. So this picture is only want to show you the condition if the HO is true. Okay, and this is the condition if the null hypothesis is false. That means there is the difference. There is a difference between mu1, mu2, and mu3. Okay, this is if the null hypothesis is true. That means there is no difference between the mean. So all the mean is same. Okay, is same. Okay, so if null hypothesis is true, then the variation in the sample means measured by MST equal to SST divided K minus 1 also provide an unbiased estimate of variance. Okay, however, if null hypothesis is false and the population means are different than MST, which measures the variance in the sample means is unusually large. So the test statistic F tends to be larger than usual. Okay, what was that mean? That means we are going to uh, uh, we are going to accept the conditions if the we are going to say that the difference is exists. Okay, the difference exists if the value of f is larger. Okay, so this is how we are going to test the f test. As I said, to get a f f value or test statistic, that is MST divided by MSE. And as I said that if we are going to reject the null hypothesis if now the f value that we calculate in this test statistic, okay, is greater than the f value alpha in the f table. Okay, so this is based on the f table, and the f table is will give you the value of p to the right, approaching to the right or the right area. Okay, so it is contra with z distribution. Z distribution in T or Z statistic test, we are going to refer to Z distribution, Z or normal distribution table, and it give you the value to the left. But now in F table, it will provide the p value to the right area. Okay. So based on the analysis of the example of the breakfast problem that we have discussed earlier. Okay, now we have convert, or when we do the calculations based on all the steps of the calculations, that is how to get the CM, how to get the total SS, how to get the SST, SSE, MSEM, MSE, how to get also the degree of freedom for both treatment and error. Okay, so we convert all the value in the table. So now this is the table. So based on the table, okay, we can see that we get the value of test statistic is 5.00. 5.00. So now you must refer to the F table. Okay, so please try to refer to the F table. And how to refer to the F table? Okay, this is the way how to refer to the F table. Okay, refer to F table and get the value of 2 and 9 for alpha 0.05. Why we must refer to the degree of freedom 2 and 9? Because based on this patient, we already get that the value for degree of freedom for treatment is 2 and the degree of freedom for error is 9. Okay, and again, I said that I want to emphasize that the degree of freedom of treatment is also referred to the degree of freedom of between group, and the degree of freedom of error is also referred to the degree of freedom within groups. Okay, and remember again, in F table, okay, they will give you the degree of freedom of the E numerator and the degree of freedom of denominator. So the degree of freedom for E numerator is referred to between group, and the degree of freedom for denominator is referred to within group. So now the degree of freedom of between group is 2. So we must refer to degree of freedom 2. And the degree of freedom of error or within group is 9. So you must find the degree of freedom that is 9. And also, because it wants you to get the value of degree of freedom based on the alpha that has been given is 0.05. So it depends on the questions. Okay, sometimes they want you to get the alpha 0.05, or maybe the other one is 0.01, because usually we are going to use these two value, that is 0.05 and 0.01 for our cut-off point for significant level. So now in this question, they want you to get the alpha level of 0.05. So you refer to the degree of freedom of 2 and 9, and at the alpha level is 0.05. Okay, so please try to check this in F table. Then you will get the value in F table is 4.26. So the F value that you will get in F table is 4.26. 4.26. Okay, so now let's compare the value that we get in our test statistic and in F table. Now the value that we get is 5.00. In F table we get 4.26. So now we can conclude that F is greater than F alpha, that is 0.05. Okay, 0.5. This one. So if F value 5 is greater than the F alpha, that is 0.05, okay, so we can reject the null hypothesis, because in this situation or in this ANOVA test, we are going to reject our null hypothesis is our F statistic value is greater than the value in F alpha or F table. Okay, so based on this example of breakfast problems, we can conclude that we reject the null hypothesis and conclude that there is a difference, there is a significant difference in average of attention spans. Okay, so that is how we are going to get the value or the results of comparison between three groups by using the one-way ANOVA analysis of CRD design. Okay, now it is not stopped here. We are not going to stop here. If we get our analysis, there is a difference. So we need to further our analysis if we are success to reject the null hypothesis, or there is a difference in the in our analysis. Okay, so if we reject the null hypothesis, okay, so we must further our analysis by using the confidence interval methods. Okay, so if a difference exists between the treatment means, okay, that means we reject the null hypothesis and accept the alternative hypothesis when there is a difference between the treatment means. So we can explore it with confidence interval. So this is the basic formula for single mean, like we have discussed in our previous lesson. Okay, and this is also the formula for the difference mean. It seems like the formula that we have discussed in our previous lesson, but in this chapter, or in this situation, the difference is only where we are going to calculate the value of S. Okay, the value of S. The value of S is refer to the square root of MSE value. Okay, and the T, this one, if in our previous lesson that is Z, isn't it? But now it is T. So the T is based on the error of the F, or degree of freedom of error, or within groups. Okay, so if we are able to reject our null hypothesis and we can proceed further our analysis, we can use the Taki methods approach. Okay, the Taki's approach for pair comparison. So what is the Taki method for pair comparison? It is the test for all pairs of population mean with an overall error rate of alpha. So based on the student touch range, the difference between the largest and the smallest of K sample means. So assume that the sample size are equal and calculate a ruler that measures the distance required between any pair of means to declare a significant difference. Okay, never mind. I have provided with you another short video about the basic explanations about what is the Taki method and why we further the analysis by using this Taki method. Okay, so this is the formula for Taki method. Okay, this is the formula for Taki method, and this symbol, like W symbol, this is the symbol when we call it the omega. So the Taki method is the formula. This is the formula of Taki method, where omega is equal to Q alpha and times by K, or degree of freedoms, and times with the value of S. S is, as I said, S now for Taki calculation method, S is referred to square root of MSE. Okay, so S divided by square root of N. Okay, so the value of the F here is going to refer to the degree freedom of error, not treatment, but refer to the degree of freedom of error. Okay, so N is the common sample size. So first of all, how we are going to get this value? This value. How we are going to get this value? So to get this value, okay, we must refer to the table 11, means the table of the Taki table. So to get the value of Q alpha, K, N minus K, we must refer to Taki table. Okay, I have provided for you the Taki table and F table. Again, I mention again, I have provided to you the Taki table and F table in Putra Blast, so you can upload and refer to it. Okay, so what we can assume if we further our analysis by using this Taki's method. So we can assume that if any pair of means differ by more than the omega, so they are declared different. Okay, so this is the further analysis based on the breakfast example. Okay, so use Taki method to determine which of the three population means differ from the others. Because in our one-way ANOVA analysis previously, we are going to, we just can know that there is a difference. Okay, we reject the null hypothesis and we accept the alternative hypothesis. So there is a difference between the three means of the three groups or the three treatments. But now, if we further the analysis, we can know which one, which pair of the group is are going to have the difference compared to the other pairing of groups. Okay. Okay. So first of all, the first step, we can further the analysis by calculate the means. Okay, calculate the means. So how to calculate the mean? This is the value that we got from our previous calculation or our previous analysis. Okay, you can refer back to the previous slides. Okay, so now how we are going to get the means for Taki methods? We are going to divide the 37, the total value, with 4 because we have four uh, 4 in a group, isn't it? If you refer back to the previous table, we have 4 in each group. So divide by 4. Same also for late breakfast, 59 must divide by 4 and 53 divide by 4. Okay, so you will get no breakfast, or T1 is 9.25 and T2 is 14.75 and T3 is 13.25. Okay, so now we can convert the value into the Taki formula. So now Q 0.5 because they already give you the alpha value is 0.05. So Q 0.5, 39. So 39. So how to get 3 and 9? 3 is, if you refer to the Taki method formula, this one is referred to the value of K. So we have 3 treatment that is equal to 3K. And 9 is the degree of freedom of error or within group. Okay, degree of freedom of error. So what we got in our previous calculation, degree of freedom for error or within group, we get 9, isn't it? Okay, so just insert 3 and 9. So now, so how to get this value if we refer to the Taki table? So if you refer to the Taki table, okay, you will get the value. This is Taki table. Okay, the DF for the first degree of freedom is 3. Okay, and then this one 9 should be around here. This one. Okay, error is also the degree of freedom of error is also referred within groups or the denominator, so it is equal. It is around here. So if you refer to the Taki method for degree of freedom 3 and 9, you will get 3.95. So now you will get the answer is 3.95. And then times with S. S, as I mentioned in this condition, S is referred to the value of square root MSE. Okay, square root MSE. So when you square root the value of MSE, okay, when you calculate the value of MSE, then you will get this one, okay, square root. This is MSE, okay, and then you square root with 4. Okay, the value of n is 4, so square root with 4. So if you try to calculate this value, the final answer that you will get is 5.02. Okay, 5.02. 6.47. Okay. So now, okay, we are going to make the comparison. So first of all, there is the possibility to compare between T1 and T2, or S1 and S2, and then T1 with T3, and then T2 with T3, isn't it? We have now 3, isn't it? T1 for no breakfast, late breakfast is T2, and full breakfast is T3. Okay, so now we are going to compare with this X is also can refer to T. Okay, or if you want to use X, is also okay for the average. Okay, if you want to use T also okay. Let's say make T1 compare with T2. Okay, and this one is you compare with T1 and T3. And what are the last comparison, the possibility of a comparison that we can try to get is to compare between T2 and T3. Okay. Okay, now I'm going to delete this because it looks mess and complicated. But again, you can use S or T, it depends on the question, because S is equal to mean, T is treatment. So you can either use of them, okay? Okay, now let's see the first comparison, that is between T1 and T2. Okay, for T1, what is the value that we are going to get? What are the value we get? The mean for T1 and the mean for T2. So the mean for T1 is 9.25 and T2 is 14.75. So how to get the difference of value? The number of the highest mean, that is 14.75, minus with 9.25. Okay, so you will get 5.55. Okay, and what if the comparison between the treatment 1 and treatment 3? So treatment 1 is 9.25 and treatment 3 is 13.25. So 13.25 minus 9.25, you will get 4.0. And the last one is between treatment 2 and treatment 3, or X bar 2 and X bar 3. So treatment 2 and 3 is 9.25 and 14.75. So 14.75 minus 13.25, you will get 1.5. So now let's compare with the value that we get in our Taki analysis. So in our Taki analysis, we get the omega is referred to 5.02. So now, okay, we compare with 5.02. So 5.5 is greater than 5.2, and 4.0 is less than 5.02, and 1.5 is also less than 5.02. So again, if you refer back in the assumption of the Taki's method analysis, okay, it stated that if any pair of the means differ by more than the value of omega, then we can declare it is different. More than omega. Okay, so now what is the value that we get more than the value of omega? So that is this one. So what we can conclude here now? So we can conclude there is the difference between treatment 1 and treatment 2 that is significant at alpha level 0.05. Okay, so if any pair of the means is differ by more than the value of omega, so we can declare the difference. So now we can declare that the treatment 1 and treatment 2 have the difference, has the different significant level at alpha 0.05. Okay. So this is also another way on how you are going to compare the sample of mean when you list from the smallest to the largest. That is one. Okay. So we can conclude that we can declare a significant difference in average attention spans between no breakfast and light breakfast, but not between the other pairs. Okay, because no breakfast and light breakfast is between treatment 1 and treatment 2. Light breakfast, no breakfast and light breakfast is equal to treatment 1 and treatment 2, or the X bar mean X bar 1 and X bar 2. Okay, so that is what is the analysis of variance or ANOVA, and they have been divided into two. That is one-way ANOVA and two-way ANOVA. And one-way ANOVA is also referred to the CRD design, and the two-way ANOVA is referred to the CRBD design. But in this chapter, we have already discussed about one-way ANOVA or CRD approach. Okay, and we can further our analysis. Okay, we can further our one-way ANOVA analysis if our null hypothesis is rejected by using the Taki method. But if we cannot reject our null hypothesis, there is no use, or there is no need for us to proceed our analysis. Okay, so that's all for today's lesson. If you have any question, you can ask me, and please refer also to the lecture notes and the other extra short videos that I have sharing in Putra Blast. There are actually 3 short videos for this chapter about one-way ANOVA. The first video is going to explain about the basic understanding on what is one-way ANOVA, and the second video will show you about the calculations of the one-way ANOVA or CRD, and the third short video is going to share with you about the Taki's approach or Taki's method. Okay, so that's all, and thank you for today's lesson, and I wish you all the best and see you.